All right, here we are in the final lecture, lecture number 12 of our series for Physics 1. So I want to end out this lecture series with something that will help you in the next series for Physics 2, electromagnetism. So there is something that is very similar and close to the first things that you'll see in Physics 2, and that is universal gravitation. Okay. So if we look back or look forward, okay, looking back to everything we've learned and looking forward into what is coming if you're taking a Physics 2 class on electromagnetism, this is something that we definitely want to talk about now. So it goes back to Newton because, again, this whole chapter is on Newton, or this whole series is on Newton's series and stuff. So Newton didn't just provide us with earthly gravitational constants like G is equal to 9.8. It's actually the solution for something much, much bigger. Newton's law of universal gravitation. So Newton didn't just do the Earth-based system, he actually did any universal gravitation, any planet, any star system, multiple masses. It unlocked the door to why galaxies are moving, why planets are moving, why the orbits are the way they are. Just an insane amount of knowledge came out of this equation. And it's rather a simple one to have. I'm just going to walk it through here for you. It's over here in the corner, and that is the force of gravity, Fg, is equal to, now I know we're used to seeing Fg as just being mg. Well, this is the full derivation of it before we make substitutions. The force of gravity is actually equal to capital G, which is Newton's constant. Capital G is just a number. It's just a constant that is given as a parameter of space. You have to have two masses, like I said in the beginning. This is a force. It needs to have two masses. There needs to be an interaction because, remember, forces are just pushes or pulls. So forces always have to have two masses. So we'll have mass 1 and mass 2. Those masses are divided by the distance between the masses squared, okay, or their radius squared. So how do we get mg? We've always used mg for Fg. Well, mg is when you're here on Earth. It's equal to the constant g, 6.674 times 10 to the negative 11th, multiplied by the mass of the Earth. Okay, so you can look this up. Look up mass of the Earth in kilograms. And then the mass of you, the person who is on Earth. You are attracted to the Earth through gravitational attraction. So this is the two masses, you and the Earth. How far are you away from the Earth? You might think you're on the surface, but you're actually, we have to consider it to be a point in space. So we are looking at the radius of the Earth. From the center of the planet, you are a radius away, right? So you are, you can look up that as well. What is the radius of the Earth in meters? And if you plug in that information, okay, if you cancel out an m on either side here, for one, get rid of the mass and get rid of the mass. So this is any object on Earth. It doesn't have to be you. It can be a big semi, or it can be a little bug. The mass on this side and the mass on that side cancel, and you get the constant g, which is just equal to what we talked about, g, mass of the Earth, over the radius of the Earth squared. If you look up these two numbers, the mass of the Earth and the radius of the Earth, as long as they're in SI units, kilogram and meters, and you plug this in and calculate it, you will get small g is equal to 9.8. It's actually very accurate, 9.81, and it continues on and on and on and on. That's why we take gravity on Earth to be 9.8. If you're looking at something that is not on Earth, but maybe in an orbit or has a great height, maybe you climbed a mountain or you're on a plane, does gravity change for you? Yeah, it does. You've changed the radius. You're no longer on the radius of Earth, you're at some new radius. So to figure out what the gravitational attraction is for you, you would need to find this new radius, which would be the radius of the Earth plus whatever height it is that you climbed. If you climbed a mountain or if you're on a plane, you'd have to add that height in before you squared it. Okay. You can think about this the opposite way. Well, first let's talk about it this way with a plus height. If you're ever on a plane, flying cross country or across the world or wherever, and for some reason you have brought a scale with you, if you climb onto the scale while you're on the airplane, you will weigh less because your height has increased. Okay, it's pretty cool that your height would actually affect it that way. If you climb up a mountain, you will lose some weight. Okay, it's not just the workout. You will actually lose some weight because gravity is pulling down on you less and less. And you can see as you continue to go higher and higher and higher in height, eventually this denominator is going to get bigger and bigger and bigger, and g is going to get smaller and smaller and smaller. Okay. Well, what heights are we talking about? So I just gave you here a quick example. At 1,000 kilometers, you're at around 7.33 instead of the 9.8. So a pretty good difference already. As you keep going higher and higher and higher, 50,000 kilometers high, gravity has very little effect on you, 0.13 instead of the 9.8, very, very little. As you get infinitely far away from the Earth doesn't have any pull on you anymore. You're just too far away from it. Okay. So here's what this looks like. We are going to talk a little bit on the gravitational field. Gravity pulls down towards the center of the Earth. It is a field that is outlined in space all around the Earth. So as you change your radius, you will see that the arrows get shorter and shorter as you go out. So towards the center, towards the Earth, they are big. As you get further away, they get shorter, which means they're smaller. Okay. This is the gravitational field. Why don't we see this? Well, when you zoom in to the top of the planet is huge. So when you zoom into the top or the bottom or the side or any part of our planet, you will see a flat surface where gravity points down in that direction and is relatively uniform in that section. This is why we can take gravity to be 9.8 at anywhere on the planet Earth. Okay? Anywhere for the most part, where it is close to sea level, something like that. We approximate it to be 9.8. And this is why people in the southern hemisphere do not fall off into space. It's because there's no gravity there. The gravity is what's pulling you to the center of the Earth. So no matter where you look on Earth, you will have this thing pushing you towards the center of it. Okay? This is important because this is a field. This is a gravitational field, which is one of the first things that you're going to talk about in Physics 2. Okay? Well, if we have a force, that means we must have an energy, right? Yep, there is an energy associated with this force. We go through the same steps as we did before, and we will get an energy, a gravitational energy, that we can use to replace our current gravitational energy. Remember, our current one is just mgy, and the g is lowercase because we use 9.8. If you want to have gravitational force on a large scale, maybe we're not talking about an Earth-based thing, but we're talking about a person on Mars, or we're talking about two planets having a gravitational pull, you will need to use the full equation, which I will denote with a capital G in the subscript here, U capital G. That is written as a negative because that energy always pulls towards each other. Gravity only works one way. There is the capital G that we discussed, which is just a constant. You'll be given it in all your homeworks, all your exams, no problems, capital G. You have your two masses, and instead of r squared, it's actually just an r. Okay, just one r for the energy. It's the way the calculus deemed it fit. And if you don't believe me and you're in the calc-based version, go ahead and perform the calculus operations needed on force to get to energy, and you'll see that it ends up dropping the square and you add a minus sign. Okay? All right, so here's our new equation. Again, we're only going to use this when we're dealing with large planetary bodies or something. But in reality, this plays an effect no matter what. So does the force. It doesn't actually matter that it is large bodies or not. It just has a very small effect on very small masses. So one way of thinking of this is that even though the planet is really big and it has the most pull, you're also gravitationally attracted to every mass that's around you. Every person that's around you, your cup of coffee or your can of soda or whatever it is, there is a small universal gravitational pull towards that object, which I think is really, really pretty cool. You just don't quite see it unless you go out into outer space where there is no other gravity but this one. All right, and just to show you that, hop on over to another YouTube page here. But here they have a small bag, I think it's of sugar, in space. And you'll see it's kind of all separated out. It's not very clear on the picture. But after a while, it all starts to kind of come together and cluster. And that's gravity acting on as this mass grows larger and larger. The larger mass attracts more and more of the smaller mass, and it accumulates and grows. I think that's pretty cool. It's an interesting one that you wouldn't really expect, but you see these masses all start to come together, and it's actually how our entire solar system was built, how all of our planets are built, how all of our star systems and everything you see in the universe was built, is through these through the gravitational force, okay, and the gravitational attraction and the energy that is associated with it. It's really, really, really pretty cool. It's how the planets were formed. There's other videos on the formation of planets as well. Hopefully I've inspired you enough to maybe go out there and check out some other videos and realize physics is kind of interesting. Anyway, the last topic, our last slide to our last video, is finally some rocket science. Now that we have an idea on how much energy is required to get us out of a gravitational field, we have some interesting bits. What speed would you need to be able to escape the Earth's gravity? It's just it's simple. It's an equilibrium problem, right? So you just want to have those two energies, the energy of gravity and the energy of kinetic energy. You want to set those two equal to each other so that you can actually escape out of the Earth's gravitational field. Okay, so it's kind of a cool little, it's supposed to be complicated rocket science, but you've learned it. You know what an equilibrium problem is, I hope, at this point, and you can set that energy all up so that we would have 1/2 mv squared being our initial energy, right? Our initial energy. We're going to launch our rocket. We're going to give it some initial velocity. Of course, we have some initial gravitational energy because we are still on the planet, so we have some of that. And we would want to set that up equal to the maximum R. How far do we need to get away so that everything drops out? The maximum R distance. In this case, the velocity will go to 0 at this distance. The Earth will be pulling us back, but eventually we'll reach 0 velocity and we'll be far enough out. So how do we calculate it? Well, we've got our equation. We want to solve for what that initial velocity is. How fast do we have to be going initially to get out of the gravitational pull? And if we rearrange this equation, we get to the second equation here. Okay, 2gme. These you can't change. 2, that g's a constant, and the mass of the Earth you can't change. 1 over the radius of the Earth. Okay, that we can't change. Minus 1 over r max. Well, what is our maximum r? What's the farthest we can get away from Earth? Well, farthest we can get away from Earth would be infinitively far away, right? Infinite. If we make this infinite, 1 over infinity, what is that going to equal? Well, 1 over a very, very large number is a very, very small number. So 1 over infinity is basically 0. So we'll do a little cheat. We'll call this 0. Okay. What that does is it just brings us into the next equation. This goes to 0. Now all we have to do is take a square root, and we have our escape velocity to escape from Earth. Square root 2 gm of the Earth over the radius of the Earth. Okay. And it's pretty cool. If you plug into your calculator, you figure out what the mass of the Earth is, what the radius of the Earth is, you'll find the escape velocity, which you should find to be about 11.2 kilometers per second. That's how fast we need to have a rocket going, leaving Earth, in order to escape all the gravitational pull. Okay, it's pretty cool, pretty cool. So there's actually a table over here of all of the different escape velocities for the different planets in our system. You'll see Mercury's is rather low. Venus is about the same as ours. Mars has lower gravity than the Earth, so theirs is lower. Jupiter is much larger than the Earth, so it has much more gravitational pull, so that's much larger. The Moon, you've probably seen the moonwalk videos. Very, very small gravity on the Moon, so it doesn't take much to get off of the Moon, which is why the moon travel, moon expeditions were so... It was an interesting fact, is I guess what I'm trying to say, with the moon experience to travel there. So we needed a lot of jet fuel, a lot of rocket fuel to get out of the Earth's atmosphere. But once we landed on the moon, it didn't take much fuel at all to leave the moon, because there's hardly any gravity to come back to Earth. Earth just naturally pulled us back for the most part. And then the sun here, the sun's absolutely enormous, 618 kilometers per second, so there isn't much that's escaping our sun. Now, there are bodies out there in the universe, like black holes, where the escape velocity is infinite. It gets too big because it's too big of a mass, so nothing escapes, not even light. But that's for another lecture, another video series. That'll be pretty cool, pretty fun stuff in that one as well when we talk about relativity. So anyway, I'm going to end it on rocket science. Of course, we'll have more videos after this on the whiteboard of all of the practices that you want to do, practice problems, ways on how to solve these things for gravitational forces and gravitational energy. And we'll end it with that one. So I'll see you on the whiteboard. All right, last chapter. Chapter 12 here of the series. We're dealing with Newton's universal law of gravity. I've got that equation written up over here, which deals with a capital G, which is Newton's constant, two masses, because of course every force requires two objects, because it's a push or a pull, and it's divided by the radius squared. A couple of constants we'll need to know are G, Newton's constant, 6.67 times 10 to the negative 11th. All this is going to be in scientific notation because these numbers are very large or very small. I also have the radius of the Earth, which is 6.38 times 10 to the 6th. And the mass of the Earth, which is 6 times 10 to the 24th kilograms. For the example number 1, I just wanted to confirm that G is equal to 9.8. We've been using 9.8 for the entire course here, and it was kind of just a given that you were expected to have G of 9.8, and that's what it was. Here we can actually confirm that it is 9.8 by doing the math for the Earth. We're going to figure out what the force is of the Earth on a person or an object or any object that's on Earth. And to figure this out, I know that that's an acceleration due to the force of gravity. So there, it should tell me, okay, I need to look at forces. And the force of gravity has an equation. So I have Fg is equal to big G m1 m2 over r squared. Now, there's a couple of things I want to change right off the bat. What are these two masses, right? I know G is just a constant, but these two masses, what two masses are affected by this gravity? Well, one of them is going to be any object on Earth. So I'm just going to make that a blank M, right? It can be a can of beans, it can be a cat, it can be a person, it can be a car. They all feel gravity the same. So that M remains open. This M is the other object. What is pulling us down? Well, the Earth is pulling us down. That has to be the mass of the Earth. And now the R down below deals with where the radius, the distance between the 2 points center of mass. Well, where's the center of mass of the Earth? It's in the core, right? Center of mass of the Earth is going to be in the core, and the center of mass of us will be just above the crust of the planet. which means that the distance between us and the core of the Earth is simply the radius of the Earth. Okay, all right, making some headway here. So we've got G, I've got ME, and I've got RE. Those are givens. M is just going to be generic, NEM, and I've got this FG out front. Now, Newton came up with this, so you got to remember Newton said that all forces can be written as MA. So let me get rid of FG since that's a force and rewrite it as MA. Okay, now we have got an M here and an M here. And since these are the generic versions, we can go ahead and just cancel that M. That leaves us with an acceleration. That acceleration is equal to G, which is a constant, 6.67 times 10 to the negative 11th, times the mass of the Earth. Mass of the Earth, 6 times 10 to the 24th. All of that is divided by the radius of the Earth. 6.38 times 10 to the 6th. And then this unit has to be squared. Okay, so I want you to figure out what the acceleration is due to the planet Earth. And I want you to actually plug it into the calculator. It's important that you go through the motions and plug it into your calculator so that you get where all the keys are located, the buttons, and how to do it, and that you put parentheses in the right place. Watching me do it does nothing. If you don't come up with the same answer I did, it means you got to learn a little bit more on what's going on with the calculator, right? All right, if you plug it in and you get an acceleration, it should be 9.8, and then there'll be some numbers going off of there. In our case, it's actually 9.83, 186 something. And the actual gravitational pull is closer to 9.81 at sea level. And that's just because I've done a little rounding with the mass of the Earth and the radius of the Earth. But it got us to our 9.8 acceleration. Okay, it's very well measured what the gravitational pull of the Earth is at sea level. As you go higher altitudes, you increase your distance r. Okay? Not by a lot, but you would increase your distance r, say in an airplane or climbing a mountain. And that then will affect the gravity that is pulled on you. Okay. So I talked about that in some of the lecture video anyway there, but you can see now how that kind of changes things. All right, so there, we've proven acceleration on Earth is 9.8. That's why we use G for everything that's on Earth. So example 2 here, we are now in a spaceship. It's orbiting the Earth at a height of 3,500 kilometers above the surface. What amount of gravity will you feel inside? Right? So what is the gravity now? Because you're no longer on the surface of Earth. You are 3,500 kilometers above it. So if we drew this out, here we have the Earth. Or the radius of the Earth is quite large already. So your spaceship is just here, traveling around the Earth, just off the top of the surface when you look at the entire planet. Not way out into space or anything, but just there. Okay, so what will you feel? What kind of gravity will you feel on your spaceship? Okay. Well, for that, we are talking about something that is in orbit of the Earth. We're talking about planets. So we should have our gravitational equation here. Okay. And again, we're looking for gravity. So I want to see what that acceleration is that I will experience. So I'm going to change FG to MA. I'm going to add G in here to be the 6.67 times 10 to the negative 11. And then I want mass 1 to be me. And I want mass 2 to be the mass of the Earth. I guess I should probably put it in variables until I finish this out. This mass and this mass will go ahead and cancel. This whole thing gets divided by the radius squared. Now the radius is no longer the radius of the Earth. We have to think, right? We are no longer on the surface of Earth. So what is the distance between our center of mass in our spaceship and the center of mass of the Earth? Well, if we zoomed in, this is your spaceship up here, right? This is the radius of the Earth, and this is your 3,500 kilometers. So the total radius from here to here would be the radius of the Earth plus 3,500. Wow, 35. I'm going to run out of space. Let me erase that here. Let me erase this. Let me start over with that. You can leave it in your books if you like. That's fine. That mass cancels. Here we would have radius of the Earth plus you need to account for the 3,500 kilometers, but it's kilometers. We need that in meters. So you need to add another 3 zeros to make it meters, and you have to remember that that needs to be squared. Okay. That's how we'll figure out what the acceleration is due to the gravity in that spacecraft. So A is what we're trying to solve. G, 6.67 times 10 to the negative 11. The mass of the Earth, that remains the same. Mass of the Earth is 6 times 10 to the 24th. And this all gets divided by the radius of the Earth, which is 6.38 times 10 to the 6th plus 3.5 times 10 to the 6th. And that all gets squared. Okay. So, gotta make sure I got my parentheses in the right spots there. And now we go ahead and we plug that one in. And you would expect it to be less than gravity on Earth. You'd expect it to be less than the 6 or 9.8. But we'll see. We'll see. So again, plug it in, plug in the whole thing. Make sure you can do it in your calculator. You're going to have a bunch of parentheses. You're going to have all sorts of things going on. Takes a little bit of time plugging all that in. Huh? Square that in the end. And there we are. We get an acceleration of 4.1. I don't want to put G. Acceleration is equal to 4.1 meters per second squared. So, a little less than half of that on the Earth. So it would feel a little weightless, a little less than normal. You'd feel half your normal weight. You could lift twice as much. It'd be very interesting. It would be an interesting feeling. Hopefully that makes sense. Right? You can use this for anything. It can be satellites. It can be the International Space Station. It can be all sorts of things. Anything that is out there. Okay. All right. Let's look at one more. Another example here of Newton's universal gravitation equation. Example 3. Gravity affects all masses, whether it's the planet interacting with us or just us with other people. So that video of the sugar getting accumulated together in the plastic bag is a prime example of that. But we feel it here. We just don't. It's not enough to register that force of attraction between two masses on a small scale, like human scale. So we'll just demonstrate that with this one. What is the force of gravitational attraction between two people? Let's say a 100 kilogram person and an 80 kilogram person that are separated by 1 meter. Okay. Well, we'll use the gravitational equation. We want to find out what the gravitational attraction is between these two people. And we'll plug in what we know. So capital G is always a constant, remains the same, 6.67 times 10 to the negative 11th. Our two masses are now 100 kilograms. and 80 kilograms. Okay, so no mass of the Earth, no radius of the Earth, it's the distance. It's just these two people, let's say they were out in space, would they be attracted to each other? Yes, so the radius squared is going to be 1 squared. And that one we can plug into our calculator, and we can see. We'll have 6.67 e to the negative 11, multiplied by 100, multiplied by 80, divided by 1. And we get 5 to the negative 7. Okay. Remember, 1 Newton is about a quarter pound of weight you would kind of go with, 1 Newton's worth. This is to the negative 7th, so this is, a million times less than that, more than a million times less. So you'd never feel it, right? But it is there. That's the interesting bit, is that even though we can't experience these things, we see them up in star systems and planets and orbits, and it relates back down to us, and it's things that we can't see, but it is there. Yes, there is a very small force of attraction between two people. So in theory, you're attracted to everything else and everybody and everything in your room. It's all being attracted together to a central point. Okay? It's just so weak that we just don't feel it. Pretty cool. All right, so our last example of the last chapter of the last lecture of this class, I'm going to do one on energy, gravitational energy. So here I've gotten the energy equation that Newton had derived. We have a negative G, mass 1, mass 2 over an R. So we've lost the square on the denominator, and we've added a negative to the equation because it always does pull towards. Anyway, for this one, I wanted to see how much energy would be needed just to increase our radius from the sun by, let's say, I originally had it for 1,000, let's say 1,000,000 meters. I mean, that's actually not even that far. We'll go 1,000,000 meters. Maybe we got some global warming or something going on, and we're going to see if we can correct that by moving our Earth either closer or farther away from the sun. Okay. So I've drawn a little picture here. We've got the sun in the center and the Earth, which is in orbit around the sun. And right now its radius is roughly 1.5 times 10 to the 11 meters. Now, this isn't exactly accurate, but it's going to work just for our Physics 1 class. Okay. So I've grabbed these numbers off of online sources. I've also grabbed the mass of the sun, which is 2 times 10 to the 30th kilogram. Again, all numbers are approximate here, just given for demonstration purposes. So how much energy would be needed to increase our radius? So we're going to have a change in energy. Okay, we're going to have a change in energy. And the only energy I want to change is the gravitational force, right? I just want to change the radius at which we pull away from the sun, right? So I want to change the gravitational force, which means I want to have a UG final minus UG initial, okay? UG final minus UG initial. And that should give me the amount of energy needed to make that change. Okay. So if I were to write these out, I would have negative G M1, M2 over R initial squared minus negative G M1, M2 over radius final squared. And that's the only thing I'm changing is the radius. Now, plugging everything in twice makes a little bit cumbersome in the calculation, so I can actually, both of these have a negative G, so I'm going to pull a negative G outside of the rest of the equation. Same thing with the M1 and M2. I have two masses, M1 and M2, and the only thing that changes here is the radiuses. So, oops, this should be final, this should be initial. If you comp that, great. So this should just be the radius final squared minus the radius initial squared. Okay, and this is just factoring these things out. So hopefully that makes okay sense. All right, so let's plug in some numbers. Let's see what we get. We're going to have a very large equation, so I'm actually getting down here. We're going to have negative g, so we're going to have 6.67 times 10 to the negative 11th. That's our negative g. We're going to have mass 1. Let's pick planet Earth, the mass of planet Earth, 6 times 10 to the 24th. Let's pick mass 2 to be the sun, 2 times 10 to the 30th. And now we have our two radiuses. Okay. So the radiuses now have to be 1 over the final radius. So the final radius is going to be the 1.5 times 10 to the 11th, plus we have now moved an extra million meters. So plus 1 times 10 to the 6th. And this all has to get squared. This is our final. Let me move my 1 to the middle there. There we are. And now we minus the initial, which was 1 over 1.5 times 10 to the 11th squared. And that thing ends in a parenthesis. All right, that's a big one. That's a big one. So I want you to go ahead. I want you to plug all of that into your calculator. This is a good test, final test, last problem, example of the semester. So plug all that into your calculator. I want to see what you get for an answer and see if it matches mine. So feel free to pause here if you need in the video. Okay, hopefully you got it. You got an answer. I had to run it through twice just to make dang sure I was right. I believe we're at 4.7 times 10 to the 17th joules to move us a million meters. Hopefully that's what you got, 4.7 times 10 to the 17th. It's energy, change in energy, so it's joules. And I like this one because it's interesting that the largest hydrogen bomb that humankind has ever developed releases 2 times 10 to the 17th joules of energy. Which I think is pretty fascinating that 2 of our largest hydrogen bombs could potentially actually move the Earth. Now, whether or not a million meters would make any difference whatsoever to our heat, that's a discussion for higher level physics, not in this class. But I did like that. You can use this as an example for a lot of different things. We don't even have to keep it to an Earth-Sun relationship. We could have a black hole and other planets and lots of other things going on for energy. Okay, well, I hope you had a nice semester. Hope you learned a lot. Thanks for sticking with me. And yeah, we'll see you in Physics 2, hopefully.